Hej, Thor.
Hej, Thomas.
Det virker.
Det virker, sørger. Jeg kan høre dig. Jeg kan ikke se dig mere. Det kunne jeg lige før.
Ja, vi har slået lige fra.
Så langt det godt. Og så vidt jeg kan se, og nu kan jeg jo ikke se dem, men jeg kan se, der vist er 16, der er logget på os ud over os. Så vi sidder lige og venter på de sidste. Daniel.
Hej, Løg. Der er fin lyd igennem.
Det er godt.
Glimrende.
Så er du imellem.
Så mangler vi bare Michael, tror jeg. Er der en af jer, der sidder i rum med Michael? Presenters. Anyone sit with Michael?
Michael.
I'm here.
That's good. I hear you at least.
I go on stage. I'm on stage.
This is fine, Michael. We just wanted to make sure that you were also online and we can see you now as well. That is great. I will mute and we will start again at 9 o'clock.
We are ready. And you hear me? Yeah.
Yes.
Hello, everyone. We are aware that it's 9 o'clock now, and we'll just give the last participants an opportunity to log on and we will start within the next minute. All right, we will start this webinar. So good morning, good afternoon, perhaps even good night to some of you, and welcome to everyone joining this webinar. My name is Thor Petersen, and I'm sitting as Vice President here with NIRAS for offshore wind. NIRAS has been involved in offshore wind since the very beginning with the first offshore wind farm here in Denmark in Vindeby in 1991. We took part of the detailed design, and a few years back we were also part of the decommissioning, a full life cycle commitment. Also today, NIRAS delivers services through all life stages of offshore wind farm, ranging from feasibility, concept and design basis, design and tendering, manufacturing, transport, installation, O&M, and also decommissioning. As is today, we have been part of delivering input to projects worldwide involving more than 45 gigawatt of capacity. This year alone, we will deliver 140 man-years of work within offshore wind to support the green energy transition, and we will continue to focus our efforts through our green transition strategy to actively support and aid the growth of renewables, and of course, work towards a sustainable future. Now, we are pleased to host you for this webinar on optimal integrity management for offshore wind farms. And for the next hour, we will be discussing aspects on how to reduce costs associated with the operations and maintenance for offshore wind farms, how we make effective the inspections of our offshore assets, how we reduce downtime for the wind turbine generators, and of course, in turn, increase production rate, increase safety, and increase reliability. Several more aspects is of course covered over the next hour, which of course and hopefully will be relevant for you. This results we will present today is a coupled approach between digital twin technology and also risk-based inspection. Risk-based inspection, sorry, that's a difficult word. The goal for this webinar, at least on my end, is that you leave here with the knowledge of the newest technologies and also best practices within the area of risk-based inspection and integrity management for offshore wind farms. Over the next hour, you will meet Michael Haubro-Faber, professor at Aalborg University. You will meet Hans-Jørgen Rieber, director for R&D activities with LIC, part of NIRAS. You will meet Paul Raymond Wagner, risk engineer with Matrisk. You will meet Thomas Bull, doing his industrial PhD with LIC and NIRAS. And you will meet, last but not least at all, Daniel Muff, structural engineer with LIC, part of NIRAS. This is a great team. I hope you will learn a lot and also be inspired. I'm sure I will. There will be an opportunity for you to ask questions towards the later stage of this webinar, and you just have to press the little button in the upper right corner where you open the chat box. You are welcome to write all along this webinar. We will collect the questions towards the end and address them accordingly. If we do not have time, we will send out a response sheet with our conclusions to your input. Last but not least, just saying that this video will also be recorded. It's already ongoing and will be sent out to all of you as we complete this day. So I will finalize my introduction and again, welcome you to this webinar, and I hope you will enjoy it. With this, I hand over to the presenters. So please go ahead. We are missing sound, I believe. Can you hear, Hans-Jørgen?
Yes.
just to present the team, which is behind this risk integrity management support system we provide. We have gathered 3 unique partners, each with their expertise to contribute to the project. First of all, LICengineering became part of NIRAS 2 months ago. We are known for offshore structural design with a long history within the offshore wind since the mid-90s for the first offshore wind farms. And we focus expertise on hydrodynamics, geotechnics, structural analysis combined with material theory. We have focused the last 6 years on structural health monitoring and digital twins. We have established a lab building our own tailor-made sensor systems, and we are experts on this area within risk assessment. And just giving the word to our other partner in Matrisk. Paul, can you introduce Matrisk shortly?
Yes, thank you, Hans-Jørgen. So I'm happy to introduce Matrisk, a company specialized in technical risk management and consulting. We've been around for almost 20 years. So next year will be the 20-year anniversary, and it's been founded by 4 partners, of which 3 professors are still actively involved in research all over Europe and internationally. And we have a global network of industry and academic partners where we apply advanced methods, but always with a very strong focus on practice and the industry. I think it's fair to say that we are experts in probabilistic inspection planning and RBI software, having developed these tools since the very beginning. And originally developed for the oil and gas industry, but now also with a strong focus on wind farms and offshore wind, of which we'll hear much more today. And with that, I'm happy to hand over to one of our partners at Matrisk, Professor Michael Faber.
Yeah, good day, good morning, good evening to everybody. Very short, here I'm representing Aalborg University in this project constellation. Aalborg University was founded not too long ago in 1974 and has already been heavily engaged since early times, since the 80s, in the development of the methodologies which are now still being applied for risk-based inspection planning. It's one of the top Danish universities, and I think it can be characterized, what is the speciality of Aalborg University is that it has a very strong interrelation with industry and has always had. So besides providing basic research, we have a tradition for a close collaboration and interaction with real world problem. It not only in structural engineering, but it's Aalborg University is also a strong university when it comes to energy in general. So with this, I will hand over to Hans-Jørgen.
Thank you, Michael. Okay, what are we sharing today? What do we provide with this tool service of risk integrity management? What we actually provide is a decision support tool for a better decision through a lifetime of a wind farm. Of course, it can be used on all offshore structures. Here we're talking about offshore wind farms. It's a tool which predict health of the structure very precisely and prevent damage on the structure. we will have a much better knowledge about the safety, and we can levelize the safety levels all over the structure. The maintenance will be more cost benefit due to intelligent inspection planning, and we will avoid failures, and thereby also addressing CO2 footprints by reduction in offshore wind. It's a solution which are state of the art, and which is first in the industry, combining these things in one tool. What are we combining here? Actually, we are taking using structural health monitoring. It's mainly accelerometers we have installed on the structures. We combine it, feed it into a digital twin, which also is known for many years. What we do here, we address it in a probabilistic approach. So we have what we call a probabilistic digital twin, which will be explained later on in this presentation. Then we get the ongoing virtual sensing by use of our dynamic measurements, and we feed that the hotspot stresses we feed into the risk-based inspection technology approach, which gives us all this I went through here on the slide here. So it's an efficient tool that allows us for much better management of our structures, and it can be one structure or a whole entire wind farm or a wind farm portfolio. I will now give the word to Paul, which will talk about the motivation for this.
Yes, thank you. So why do we do all this? So what's the main motivation behind it? So generally speaking, it's fair to say that offshore wind turbines are placed in pretty harsh environments. So they are subject to cyclic wind and wave loads throughout their lifetime. And it's well known that these types of loads, in particularly steel structures, over time lead to fatigue damage. So that is accumulated damage that doesn't immediately show, but over time can become problematic. And in the worst case scenario, if these damages remain undetected, they can, in the worst case, lead to failure of the structure, or at the very least to unplanned production outages that have to be accommodated in order to address these damages. And while wind turbines are typically designed for 20 to 25 years, considering fatigue damage, so this is not something new, this has been known for quite some time, there are mainly two factors that have to be considered, or two scenarios that have to be considered, that make fatigue damage, where fatigue damage plays a very important role. And one of those is the potential for lifetime extension. So when our wind turbine enters or nears the end of its planned lifetime, we want to have a set of tools available to accurately judge whether it's safe to continue operating that turbine beyond the originally planned lifetime. And the second scenario that is of importance is extreme wave events or extreme storms that can hit our wind turbines and can unexpectedly lead to an accumulation of damage that was not anticipated at the time of design. And the underlying motivation behind behind our endeavors to properly manage those fatigue damages is the fact that the number of wind turbines has been steadily growing. Offshore wind turbines has been steadily growing over the last years. As mentioned earlier, the first example of the first offshore wind turbines were built in the 90s, but you can see from this graph that the number has been growing dramatically since then. And the second thing that you can take away from this is that I mentioned before that most wind turbines are the lifetime of what most wind turbines is around 20 to 25 years. You can see from this graph that in the next years, the first substantial number of wind turbines will approach the end of their lifetime, and the question of lifetime extension becomes a pressing one. Now, another thing that we can consider, so you see from this graphic, you see the number of installed turbines currently in the different construction types, and we can see that with the announced turbines in the coming years, we expect completely new technologies to also enter the market and to enter operation. And we just mentioned here that the approach that we will present to you today is applicable to, or will be applicable also to these types of structures, so to cable fatigue problems in these new types of offshore wind structures. Now, one other thing to keep in mind, and this was already mentioned before by Hans-Jörn, is our goal is not only to monitor or to model and consider single wind turbines, but we really want to emphasize also the farm level considerations. So there are two things that come to mind here. The first thing is that if you plan, or when you jointly model turbines in a farm instead of just modeling them individually, you are able to transfer insights from modeling one turbine to all the other turbines in the farm, just by a matter of gaining expertise in this field. But the other thing is statistical dependency that we can expect from multiple turbines in a farm. So you can think of the loads, for example. The loads in a given wind farm are not completely independent of each individual turbine. So if there's a large storm that hits a wind farm, it will affect most turbines in a similar manner. And considering these dependency effects has a strong effect on the estimated failure probability, or the estimated potential loss of operationability of turbines in the wind farm. And for that, we have a very small example here on the right-hand side, where we show that the gray line is a case where we do not consider dependency between individual turbines. So we assume that a turbine has a design fitting annual failure probability of 10 to the power of -4 annually. And you can see that the expected fraction of portfolio loss is very small compared to the fact where you actually consider correlation between these failure events, up to the point that in the case of a correlation of 0.6, we expect with a probability of 10 to the power of -4, we would expect a 40% portfolio loss, as can be seen by this violet curve here. Now, to wrap it up and to start a more technical part of this webinar, well, our main goal and our main service book that we want to provide to our clients is to offer tools for prediction and prevention of such failure events, fatigue failure events. And on the prediction side, now the important thing is to be able to accurately model the behavior of our structures. And for that, we use a set of advanced monitoring approaches, structural health monitoring approaches, and we use that to construct what we call a probabilistic digital twin. So that is an enhancement of the digital twin that considers uncertainties in the digital twin replica of the structure, and we use that to predict the performance of the turbines. And on the other hand, we have and using this information, we move on to prevention, where we use the predictions from the digital twin to estimate the reliability of our structure, but then also go into a proactive manner into the scheduling of the inspections in order to keep our structures operational and reliable over the lifetime. And with that, I hand over to Daniel from LICengineering.
Thank you, Paul. I will be going through in a high level, the structural health monitoring and also our probabilistic digital twin. So this will be a high level overview of these two concepts. So first of all, what is structural health monitoring? Well, in essence, it is the capturing of data on, for example, civil structures. And this is important because these may deteriorate due to corrosion or fatigue over time. And we want to get a handle on that, of course. Examples of data that could be collected would be SCADA measurements or the measurements of the structural response of the system. And having this data allows us to, in real time, have a good estimate on the damage accumulated by the structure so far and the remaining lifetime in it. And it also allows, in that sense, for timely maintenance to prevent failure to occur, of course. So the overall objective is to increase safety and reliability of the civil infrastructure. And how we use this information in our setup is first and foremost we try to identify the system. We do that from the measured response, and in our case we apply an operational modal analysis to the system and obtain the modal parameters, an estimate of the modal parameters. These modal parameters can then be used to update a virtual model of the system. In our case, this will be our probabilistic digital twins. And we can do this in real time, of course, so we have a real-time virtual environment in which we can simulate. So this simulation in the virtual environment allows us, of course, to also employ virtual sensing schemes, which allows for estimates of quantities of interest in locations in the structure, for example, that we're not able to directly measure. And typically we're not able to directly measure in fatigue hotspots. And in the case shown in the picture to the right, we have a fatigue hotspot at the bottom of the wind turbine, and we have acceleration measurements in the tower. And by employing virtual sensing schemes and a virtual representation of the model, the digital twin, we're able to get a good estimate on the hotspot stresses. And these stresses, of course, feed into damage estimation and also a risk-based inspection, which will be presented shortly. So the digital twin, the second pillar here, what this is as mentioned, a virtual representation of the physical asset, and we're able to update it from real-time data. And the environment in which we can simulate this virtual or this digital twin allows for crucial decision making, making the right decisions. And finally, the SHM informed digital twin here is briefly summarized in the figure to the right, where we have examples of the data captured by a health monitoring system, which could be SCADA and the structural response. And that feeds into having an up-to-date digital twin, incorporating uncertainty in the model parameters. And that allows us to then, by employing virtual sensing schemes with the measured response, get stress estimates incorporating these model uncertainties. And then by feeding these stress estimates into a risk-based inspection approach, we can get a good estimates on risk-based planning. So yeah, to summarize, the combination of the SHM and the probabilistic digital twin as well as RBI allows for well-informed decision making, and then risk-optimized maintenance strategies, and so that we can finally maximize the utilization of our asset. And then I believe I'll hand the reins over to Michael Faber.
Thank you very much, Daniel. I don't want to spend much time on this. I just want to set RBI for offshore structures, wind turbine systems into the perspective of integrity management. So integrity management is tremendously important, not least here in our challenge to become more sustainable and more resilient as a society. When we are dealing with offshore structural systems like wind turbine parks, we are dealing with degradation processes like fatigue and corrosion in combination with extreme load events. That in principle 2 ways that we can manage the integrity, and one way is what we are utilizing heavily here. That is to collect information on the actual performance of the structures throughout their lifetime. And that concerns not only the direct development of damage, but also performances and the load environment, as we have already heard a little bit about. It's essential that we are cost efficient, of course, but it's also essential that when we maintain the integrity of structures, that we have an adequate level of safety and reliability. The reliability of the structures goes into the context of the reliability of the energy provision in the end, as we will also talk about a little bit in the concluding remarks. Of course, safeguarding life safety for those persons who are also involved in the operation of the wind turbine parks is very, very important. The inspections, they facilitate that we can intervene if something is not going adequately with the performance of the structures. And thereby we can, by timely interventions, we can reduce consequences and also enhance the overall reliability and safety performances. I don't want to talk much about the history, but maybe just one word, which means a couple of words. RBI, I think it's fair to say that it takes its origin from the aeronautics already in the 1970s, and also DNV, De Norske Veritas in Oslo, Henrik Madsen and the people around him, they were first movers to get risk-based or risk-informed inspection planning into practice in the offshore integrity management context. Aalborg University, as well as Technical University of Munich, was also strongly involved in the early phases in the end of the 90s, beginning of the in the end of the 80s, beginning of the 90s, and also NTNU, the people around Torgeir Mohn, they contributed substantially. In the beginning, it was quite, let's say, demanding in terms of required expertise to actually model and analyze the risk-based inspection plans. Later on, maybe especially towards the end of the 90s, the beginning of the 2000s, when I was ETH, I was a professor at ETH, we took an important step to make risk-based inspection planning less complex, so that normal offshore structural engineers could actually do it. And that was a great success. And it has been applied, so indicated in this slide here, for numerous installations around the world since that point in time. It also indicates a little bit that we have collected over the years a substantial amount of experience on actually how to do it, what problems we can expect to encounter. Of course, we have refined different parts of the models over the years as well. And not least here within the last 5 or 6 years, we have now substantially improved fracture mechanics model, which also reduces the uncertainties in general. So now I would like to give the word back to Paul.
Yeah. So we thought it was a good idea to not only talk about RBI, but to actually give you a very simple example of RBI, or how it, to show you how it works and what it does. And for this very simple example, we are just considering a single hotspot in the wind turbine, and we can see in this plot. So this is basically the core plot that you will stumble over very frequently when dealing with RBI planning. You can see on the x-axis you see time. So this hotspot, or this wind turbine, was installed in the year 2000, and we can see on the y-axis the annual failure probability. And in this case, we assume that each year the structure is subject to a constant stress spectrum, and due to the uncertainties in our system model, or in our turbine model, the annual failure probability can be calculated, and we can see here in this case that the annual failure probability increases up to the point of around the year 2023, where it first crosses this threshold of 10 to the power of -4 of the annual failure probability that is considered safe, a safe operational condition. Now, what happens if some extreme event affects the structure or hits the structure? Consider a storm, and storm is just a placeholder for some extreme weather event that leads to extreme loads on the structure. And consider such an event hitting the structure in the year 2007. Now, what this will do is it will increase the annual failure probability in that year, but it will also lead to a shift of the annual failure probability in the subsequent years. And the result of that is that we cross this failure threshold not in the year 2024, but already 10 years earlier, around the year 2016. And of course, you could now say, as an operator, following following the occurrence of the storm, you go out and you inspect the structure immediately to see if any damage has occurred in your support structure. And the effect on the annual failure probability would be as follows. You would, by going out and inspecting the structure, there are basically two potential outcomes. So either you don't detect anything, which means that your prior assumptions on the mod structure were a bit too pessimistic, or you detect something and you repair this damage, which will also lead to a higher reliability of the structure in subsequent years. But this crude approach of reacting on events is not optimal, because you actually have, even after the storm, you have some years that still admit a safe operation. And what we offer with this RBI approach is to automatically schedule inspections such that they take place exactly after or before in the year before we actually cross this failure threshold of 10 to the power of -4. And of course, with this approach, in case another storm of that magnitude hits the structure, we'll be able to schedule inspections adaptively and continuously to always kind of be ahead of the curve in that sense. Okay, with that, I want to hand over to my colleague Thomas.
Yes, hello. So I will present how we can combine this in a kind of integration levels. So we have the possibility of having no structural health monitoring system. This is what is mostly done today. So you have some prior model assumptions you use for your typical conservative model assumptions, which you use for your stress estimation. And this is what is typically done in a design phase, part of the approach. And then we have level 1, which we call a temporary SHM system. Here we can do the model updating, but we can't use the measurements for actual stress predictions. So here we need some load assumptions, mid-ocean data. And then finally, we have the fixed SHM system, where we both can do the model updating and the stress predictions by virtual sensing. And then on the right, I tried to sketch that for each level, we have an increased cost for the proactive measures, but we also have a decrease in the uncertainties for each level. So, then we try to illustrate each of these setups. So we have the first ones, where we have the prior models that feeds into your structural solver, together with your mid-ocean data and wind data. And then you get some stress estimation based on these load assumptions. This is subject to rather large uncertainties, which can be potentially conservative. Then we have the temporary system, where we have the structural health monitoring system measuring, as we discussed earlier, the accelerations and scalar data. Then we can identify the model parameters, and then from the prior model assumptions, then we create a model database of possible structural realizations. We map these two together, so the model parameters of the database and the model parameters of the measurements, and then we update our prior model to a posterior model. So we get a set of models that can actually fit the data. Then we feed this into our structural solver together with the mid-ocean data, and then we get an inspection plan which can fit this data. And then finally, for the fixed SHM system, we have the structural health monitoring data also feeding into the stress estimation. So we use the accelerations to estimate the hotspot stresses in a similar manner as for the temporary SHM system. So we did a small case study. So we have here in the design phase, so we typically use a DFF of 3 with no inspections for example, a monopile design here. But I tried to use also a DFF of 2 and a DFF of 4 to see the difference in mass for these structures. And then we compared to the RBI plan for these 3 types of structures. So we already in the design phase, we can actually find an optimum for the operators between the expected OPEX and the CAPEX used for these structures. So this can be independent, I guess, from operator to operator. And then finally, we try to simulate what sort of information the SSM system can provide. And here we get a reduction on the inspections in around 30% from this uncertainty reduction on our stress estimates. And on top of this, you also have that the prior model assumptions are typically conservative, which is why we may even get fewer inspections in practice. But on the other hand, if we have any non-conservative design assumptions, then this is also captured by the SHM system, as Paul illustrated, and then inspections, they will be scheduled accordingly. So I will give the word back to Hans-Jørgen.
Yes, thank you, Thomas. That was a nice explanation of the probabilistic digital twin. So just to sum up, that we have presented this novel tool service, what you call it. The novelty lies within the combination of 3 different technologies: the structural health monitoring, the digital twin, and the risk-based inspection approach. And the second novelty lies within that we enhance the digital twin by giving it a probabilistic approach, which is a novel thing to do. This gives us a very strong decision tool. So we can reduce cost and save money for generating offshore wind energy, electricity. You will be able to plan for a extended lifetime already for a new wind farm by applying this, so you can extend it and include that in your business plan, and it will be a much better business plan for the investors. You can also on existing old wind farms apply this system, and you can, by use of a measurement campaign, back calculate and recalculate fatigue damage, and then apply a proper inspection planning to extend the lifetime of the old wind farms. Furthermore, by investing in this, you can collect all data systematically and use it, for example, in due diligence in a selling buying situation, or in insurance issues. So it's a very strong tool, and it's also the best practice seen from the third-party authorities. So we can only recommend this for the future design. You'll also be able to feed all these information back into your next designs, because you have so much knowledge gathered from this, and both your design will be more optimal in the future, and your design basis. For this, I will hand over to Michael just to give some future thoughts about developments. Thank you, Michael.
Yeah, much, Hans-Jørgen. With this slide, I actually just want to point at the fact that this is not the end of the line. This is a fantastic development, and representing academia in this project, I'm of course thrilled to see theories and methods and rationales being applied in practice. But there are, of course, a lot of further developments in the horizon, and some of those are already well ongoing. They are not part of an industrial service as it stands now, but they will be within a very short period of time. We need to consider these energy systems to be a strategic part of the energy provision in general, and this is strategically important for society, that we have an adequate level of not only reliability but only resilience. That goes for stakeholders on the side of society, but of course also for the owner and the operator. In those developments which we have ongoing, we are considering wind turbine parks as systems of systems, not only looking at foundations or shafts, but looking at all the bits and pieces comprising the individual wind turbines in combination, the cables, the substations, and everything. And we can model the performances of these systems of systems and benefit in actually modeling the resilience performance of the systems, the reliability of the energy provision, the optimal stock keeping of spare parts, and so on. It's super exciting, and these future developments will just add to the benefit of using a digital twin SHM risk-informed approach to the overall integrity management. I think with this, I would like to give the word to Thor. Thank you.
Thank you very much, everyone, for making your great contribution here to this webinar. We have finalized the presentation part of the webinar, and we will now open the Q&A session, and this will allow you to interact with the speakers here, which will come online when we direct the questions to them, so you can see them and hear them speak at the same time. Firstly, I will open with a general question, and then I will take the questions we have received in the chats. And currently I count 5 questions we've received during the webinar, but please, the the poll of questions is still open here, so you're more than welcome to address your considerations now. But my first question goes to you, Hans-Jørgen. I do understand that there is a huge benefit in coupling this digital twin technology with risk-based inspection and structural health monitoring, and also probabilistic design, listening to these presentations over the last half hour. That could be insurance related, it could be extended life, safety, and many other aspects. But why this service, and why is this technology unique?
Yes, thank you, Thor. Yes, the uniqueness, it has been known, frankly, for many years in the oil and gas, but not in this unique combination, as I mentioned before. It is so obvious that the owners and the operators, society will save money applying this system. It's very low cost to apply a few accelerometers on your structure and feed it into a digital twin or a final element model. You tune into digital twin and apply this. It gives a much better view of the safety of your structures, and you can levelize the uncertainties and the safety levels by kind of having a pause in some of the structures during storms where you may have overproduction in energy. So you can in that way also tune the whole wind park to a same level of safety. But the big upside is in the lifetime extension by using of either reducing the design strength, not as today engineering, but that will again induce changes to the design rules, which takes a long time. So for now, we should take it into account that we can extend the lifetime applying this on new wind farms, and then take the benefit of the longer lifetime and the better business plan or business for each of these projects, and in the end a lower price for energy. Yeah.
Thank you very much for that elaborate answer. While I have you here, Hans-Jørgen, I do understand that these implications could be considered in several aspects in relation to the phases of the offshore wind farm, but when should it be implemented most effectively? Is that in the planning and design phase, or is it later on?
Yeah, it's a good question, and we had also this question from the public. I can remember was from Torben or someone else, and Paul answered, and I'll just rephrase that we of course we would like to apply this from the very beginning. Of course, it's obvious, but for old wind farms like 18 years old, you can apply this. If the lifetime is planned to 20 years, you have some years to do measurements. You can back calculate and recalculate the actual fatigue damage, and then you can apply a proper RBI and then do a few inspection, and thereby most likely extend the lifetime for already installed wind farm, which is just additional profit for the business case. So it's of course best from the very beginning, but there's a big uptime also, upside doing it on the old turbines and wind farms.
Thank you very much, Hans-Jørgen. Then I will take my liberty to jump to the questions we've received during the presentations here, and some of them have been replied, but I think we take them anyway. The first questions I will take is from Torben, and that goes to you, Paul. Are you considering all parts of the wind farm in the evaluation, and not only the support structures, i.e. also cables, OSS, RNA components?
Yes. So yeah. So thank you for this question. So this at so the short answer is no, but the long answer is not presently. So we are aware of this, and we have started developing, have started first test cases on considering this, but presently this is not at the stage where so it's at the prototyping stage, I would say. But our approach in general is completely applicable to all of those systems or system components as well. So it's not restricted to the support structure. It could be applied to other parts of the wind farm equally well.
Thank you, Paul. While I have you here, I have a question to you as well from Giovanni. And Giovanni asks, some existing offshore wind farms have run most of their life without HSM systems. For these wind farms, would it still be worth installing an SHM system in the last 2-3 years of the original design life, back extrapolate the data to the already elapsed life?
Yeah, so that's I mean I think like Hans-Jørgen put it, of course yes, but the reason for that is of course you want to gain as much information about your structure as you possibly can. If you missed, quote unquote, missed the chance to gather this data from the beginning, it's always better to gather it rather late than never, because of course you can use this data, this information together with statistical approaches to back calculate and have a much better estimate of your local conditions than just some generic broad assumptions that you would make otherwise. So any data collection is good in that sense.
Thank you, Paul. I'll let you off the hook. The next question is from Arifian, and that's on structural health monitoring. I believe it's for Daniel, Thomas, or Mikael. Will HHM information used to update parameters in probabilistic fracture mechanics model? If yes, what kind of parameters will be updated? So I'll leave that up to you three. Who wants to answer that?
Well, I already wrote a super short comment to this, so let me take it in short now. The SHM is utilized to update the probabilistic representation of the dynamic system properties. For instance, the probabilistic model of the stiffness of the soil, and also the uncertainties associated with the fatigue loading. So that's how we do it. And now, while we are at it, I might continue that can be done. So with respect to the dynamic system properties, using SHM, we can update this at any given point in time during the measurement campaign. It does not need to be continuous, but for what concerns the stresses, we need some continuous measurements. It does not mean that if we have a broken series of measurements, we are not able to take that into benefit in updating our probabilistic model of the fatigue stresses. But the more measurements we have, the better.
Thank you, Mikael. Maybe while I have you on, you could take the question from Torben as well. Are you considering degradation due to corrosion in the life estimates? And if yes, how do you correct?
No, in the present setup. So corrosion as a degradation process in itself on these facilities has of course to be managed, and there are different strategies for doing it, protection strategies, inspection in combination with for instance anode systems, and that has to be managed. It's not a part of this setup, but of course we can also provide this service based on the experiences we have with similar issues from earlier from the oil and gas industry. So when it comes to the effect on fatigue degradation, so the combination of corrosion and fatigue degradation, it can be accounted for, and it is accounted for in the modeling of the fatigue crack growth in the fracture mechanical modeling setup.
Thank you, Michael. I think we have time for one or two more questions, and I will direct the next question to Daniel. If some of the parameters are updated continuously, as it means structural analysis is also performed at every update to get the new POF.
Yeah, thank you, Thor, and thank you for the question. Yeah, in principle, yes, that could be done. I think it's up to the end user how often do you want to get an update of your probability of failure in your system. But you could do that as often as you have new data.
Thank you, Daniel. And the last question we have time for is from Elvin. So I'll pose that to you, Thomas, and you're welcome to push back if you don't find you want to answer that. What are your view representative locations within a wind farm for the application of SHM, spatial water depth, etc., and how many SHM positions? Oh, that just went away. SHM positions do you generally recommend within a wind farm?
So for the application part, I think all water depths and support structures are applicable for this. We need something on the floating, but it should be directly applicable from what we already have. And then the amount of positions. So a few structures provide pretty much information due to the correlations between the structures, both loading and also welding and fabrication considerations or correlations. So one structure or two structures in a farm should provide a lot of information. So you don't need to monitor all of them.
Thank you very much, Thomas. That concludes our presentation, also the QA session. We are closing very rapidly towards the end of this webinar, so also allowing you to go to your next meeting. I will just do a short closure and summary. During the last hour, we've heard about structural integrity and reliability and how that can be used to effectively handle various aspects, sort of prediction of the lifetime of your structures and also prevention of failure events. We heard about structural health monitoring to increase safety and also reliability. We heard about integrity management, also in conjunction with the challenge to become more sustainable in the future, dealing among other things with degradation processes. We heard about risk-based inspection. We saw a case study, an example, and last we discussed the extended lifetime possibilities using these technology. I hope it was very informative and also inspiring. I want to extend a big thank you to the presenters who joined here and shared part of their very specialized and dedicated knowledge in this area. It is a detailed and dedicated service. And as I hear, and you also hear, they do have the knowledge and experience from various offshore structures. So don't hesitate to contact me or either one of them from the team if you want to learn more. We will collect the questions you post to us here. We will give our replies and we will send them back out to you. We will also send you the video recording of the webinar. And again, don't hesitate to reach out. It was our utmost pleasure to host you here. So again, thank you for taking the time to join, and thank you again to the presenters. Have a nice day.